One of the most important discoveries in the history of our physics is the nature of the motion of the planets around the sun. I think many people don't realize this, but the question about the moving objects in the sky goes back as far as 300 BC. And Plato questioned how we might explain the motion of wanderers in the sky, so-called planets. Ancient astronomers had realized that the stars in the sky are fixed in their positions as they rise and set over the course of an evening, and you could make patterns out of them and shapes and recognize them and name them for creatures and mythical beings. But among those fixed stars, there were individual points of light that would wander through the night. Though they give it the name wanderer in the Greek, known as planets. I could go on and on about the history of our understanding of universal gravitation. In fact, one might consider dedicating an entire course to the study of universal gravitation. But here, I'm just going to give a brief history, very quickly, of discoveries made by Copernicus, Kepler, and of course, Isaac Newton, whom we rely upon so heavily, and how they helped us to our modern understanding of the very important physics problem of the motion of the planets around the sun. I'd spoken before about the role that Aristotle played in our understanding of inertia. In fact, in the context of Aristotle, our lack of understanding of inertia, Aristotle believed that it was the natural tendency of all objects in our universe to ultimately come to rest. Thank goodness Galileo fixed that idea and made it possible for Isaac Newton to give us the three laws so that we have a proper understanding of the mechanics of our universe. Nevertheless, it was Aristotle's view that it was the natural tendency of objects to be at rest, and if they weren't at rest, there must be some influence or impetus that caused them to not be at rest. A natural conclusion that you might derive from that, if you were an ancient philosopher, is that since we, standing on the surface of the earth, cannot feel the influence on the earth that would put the earth into motion, then the earth must itself be at rest. Then when you look up into the sky and you see the motions of all of the planets and the stars and the sun, the moon, and the sky, then naturally you come to a conclusion that if you were to draw a model of the solar system, you would put the earth squarely at the center, and then all of the planets would move about the earth. And so this is what ancient peoples believed as part of the Aristotelian physics, with the earth central to the solar system. It's interesting to note here that when this idea was first proposed, the earth at the center of the universe, it was a purely scientific idea. Granted, a bad one, but it was a purely scientific idea. And then later on, those ideas were changed. And it wouldn't be until a significant amount of time had passed before the notion of the earth being at the center of the universe became a religious idea, which changed the character of how that scientific idea intersects with society. So it was a very, very long time after Aristotle had proposed his notion about the natural tendency of objects and the idea of the earth being at the center before we finally got it figured out. And that story is a fascinating one. With many, many characters and lots of interesting twists and turns, including many of the people that you may have studied about in courses on Western civilization. Nevertheless, I'm going to leap ahead to where we finally started to get this problem fixed. Nicholas Copernicus, who lived from 1473 to 1543, was surely the first to get this idea that the Earth could not be at the center of our solar system. By this time, models of the solar system had been created based on the Earth being at the center, had become enormously complicated. As a reference, you could look at the models created by Ptolemy. Very, very mathematically complicated. There's a principle that had arisen by this time known as Occam's razor. And the idea behind Occam's razor is that the simplest solution to a problem was likely to be the correct one. And Copernicus realized that if you were to instead put the sun at the center of the solar system, that you would in fact have a much easier time describing the motions of the planets in the sky. The trouble for Copernicus was that by this time, that idea had become a religious idea and not necessarily just a scientific one. And so saying so out loud would have been would have made Copernicus's life very difficult, because God put Earth at the center of the solar system, and to say otherwise would be heretical. So he did a rather clever thing. He waited until he was just about dead, and then he wrote his book De Revolutionibus. I think it was 11 volumes worth of book that he published at the time of his death, proclaiming that, in fact, it was quite obvious, based on what was known at the time, that the sun must be at the center of the solar system and all of the planets must go around it. And he presumed, by the way, that they went around in circular orbits. Here we see an artistic rendition of him here with a page from his book, where he's drawn the sun at the center of the solar system, and then perfect circular orbs around the sun, which were the orbits of the planets. So you might think, well, finally, good, somebody has the right idea. This is a dramatically different idea, a revolutionary idea, you might say, that should fix the problem straight away. But it turns out it didn't happen that way. Copernican ideas, of course, were blacklisted by the church, and the ideas did not immediately catch on. They were certainly considered heretical, and therefore they were discredited. And it would be quite a bit of time before Copernicus would take hold. And in fact, there is one individual who really is responsible for making the transition to the realization that Copernicus had the right idea. Johannes Kepler was a German astrologer who was not of great scientific account. In fact, mostly we regard his early career, he was basically a math teacher, a high school math teacher in Prague, the equivalent of high school. And he was a man of very, very singular mathematical brilliance, but he was unsuccessful professionally for quite a while. And secretly, he was a Copernican. He had read the works of Copernicus and understood the simplicity of the notion of putting the sun at the center of the solar system. And he wanted very much to demonstrate that that idea was mathematically correct. His struggle, however, was that he had no data on the positions of the planets, no reliable data that he could use to match his mathematical equations to. And it turns out around the same time, a fellow by the name of Tycho Brahe, who was a Danish astronomer, was collecting some of the best astronomical data that had ever been collected. It's important to bear in mind that this is before the advent of the telescope. This is all happening in the early 1600s. By the way, Kepler lived from 1571 to 1630, just to give you some idea, as we enter the Renaissance period. Tycho was making fantastic measurements of the positions of the stars in the sky, not with telescopes. Telescope hadn't been invented yet, but with what are known as transits, large bits of metal, very much like protractors and so forth, mounted to great stones with angle measures on them and so forth, so that stars and planets could be sighted in the sky with better precision than had ever been done before. So it was actually very much exactly the data that Kepler needed to do a bit of mathematical brilliance. The trouble was that Kepler and Tycho didn't get along very well. And so it wasn't until Tycho's death that Kepler finally got hold of that numerical data, and he was able to make some brilliant mathematical observations about what those astronomical observations had to say about the motion of the planets around the sun. It was immediately apparent that Copernicus was right, and now Kepler had the proof. So what he did was he put together the ideas into what are now known as Kepler's 3 laws of planetary motion. Kepler's observations can be summarized in this way. The very first is that by looking at the experimental data, it was clear to Kepler, and he could demonstrate it mathematically, that the motion of the planets around the sun were not, in fact, circular. For a long time, it had been held that circles are perfect. We love circles because we inscribe inside circles right triangles. Based on right triangles, we devise all of trigonometry. We make the assumption of right triangles everywhere in our math, science, and engineering. And so we're all about circles. But Kepler had realized that the orbits of the planets around the sun could not possibly be circles, but in fact were ellipses. And this is not surprising because around Kepler's time, in the early 1600s, what are known as conic sections became all the rage. If you've taken a course in calculus, then you know that conic sections are often discussed in terms of the functions that are most useful in the application of calculus. Anyway, so Kepler was familiar with the conic sections, one of which is the ellipse. And he realized that the best way to fit the experimental data that he had was to assume that to suggest that the planets were elliptical. I was going to say assume, but it's not an assumption because there's experimental data to support that idea. The next thing that he discovered was a little bit curious. He realized that if you were to draw a radius for the orbit of a planet as it goes around an ellipse, that the radius of that orbit sweeps out equal areas of orbit in equal times. Now, that's not something I'm going to demonstrate with equations or anything in this particular discussion. And it's not one that in this course we'll necessarily use for calculation. But he had discovered something really powerful that he didn't realize. It's a consequence of what is known as the law of conservation of angular momentum. The important point for our discussion is this. What Kepler noticed was that when, if the orbit of a planet around the sun is an ellipse with the sun at one focus, that means the sun is off-center from the ellipse, that when the planet is furthest away from the sun, it travels the slowest. And when the planet is closest to the sun, it travels the fastest. First is the revelation that the speed of a planet in its orbit around the sun is not constant. But the second revelation is that it moves faster nearest the sun and slowest furthest from the sun, which is a significant observation and one that was important for Isaac Newton. The third one I personally find amazing. Kepler had data for all of the planets that were visible in the night sky at the time. Remember, there were no telescopes yet. And so the only planets that we were aware of were the ones that you could see with the naked eye. And so for all of those planets, he looked at all of the data and he realized something quite remarkable. That for every planet that he had data for, if you took the time period of that planet's orbit squared, that is, the amount of time it takes to orbit the sun once, divided by the average radius of its orbit cubed. Of course, if the motion of the planet is an ellipse, the orbit gets larger and smaller during the motion. But if you take the time period squared and divide by the radius cubed for each planet, you get the same number. Kepler was a bit of a numerologist. He thought numbers were sort of the voice of God, and he was interested in every number, and he may have felt that every number that you could calculate had some sort of a physical meaning. He must have found this astounding. The time period squared divided by the radius cubed is equal to a constant for every known object that orbits the sun, including the Earth, by the way. What a remarkable revelation. The important thing to get about this is that if you imagine yourself around this time and Kepler comes and talks and explains that the observations that have been made of the planets lead to these three conclusions, you might raise your hand and say, okay, fine, this is what happens. But why do they behave that way? Why should it be that the planets move in ellipses? Why should it be that they move slower here or faster there? Why should it be that the time period squared divided by the average radius of the orbit cubed be equal to a constant? Why? Kepler's answer would have to be, I would imagine he would give a lengthy one, but his answer would have to be, I have no idea. This is simply the way it is, based on the observation. At this point in history, Kepler's three laws are an observation, supported completely by evidence, but with no explanation whatsoever. Why should it be so? Is a very, very compelling question that was taken up by Sir Isaac Newton. Between the summer of 1665 and the spring of 1667, Isaac Newton had his very famous two productive years when he was fleeing the bubonic plague. He had been studying at Cambridge when the plague arrived in 1665, and he fled to a family farm to sort of ride it out. That plague ultimately would kill a quarter of the people in London, about 100,000 people in Europe. So Isaac Newton was off hiding from the plague, and he began working vigorously on problems that he had been considering for a while. And of course, he gave us the three laws of motion, which is how we understand how the constraints and conditions that act on objects create acceleration. And from the acceleration, we can determine the motions and predict the future, a remarkable achievement. We did a great deal more while he was in isolation. He also worked out quite a bit of optics and fluid dynamics, and as it happens, the problem of gravity. Isaac Newton, being a scholar, was aware of everything that had come before, and he sought to find that explanation. For if the motions of the planets around the sun are ellipses, what is the cause of the motion? Well, it's Isaac Newton himself who sets the construct for how we determine such a thing, Newton's second law. If the orbits of the planets around the sun are indeed ellipses, then it should look something like this. Here I have an ellipse drawn with the sun at one focus. The sun is not at the center of the ellipse, but as you probably learned in very, very, very early math classes, an ellipse is drawn by taking the locus of all points that are whose sum is a constant from two foci of the, well, it's a complicated idea and challenging to say, but you might remember putting two tacks into a piece of paper and tying a bit of string to it and hitching a pencil into the string and going around, and it makes the shape of an ellipse. So here I have the sun at one focus of the ellipse and a planet that is in orbit around the sun. You see at some point in the orbit it comes closer, at some point in the orbit it is further away. When it is closest it moves faster, when it's furthest it moves slower. And it has a velocity, which I've labeled here the vector v, which is tangent to the orbit at all points. So Newton's task, the problem that Newton is interested in solving, is what would be the nature of a force that would cause the alteration of that velocity, that is, cause an acceleration, that would produce an orbit that it was in the shape of an ellipse. It is an extraordinarily daunting task, because you see, what is going to happen to this situation as I've drawn it is in the very next instant, the planet will move along the orbit. Four things will occur. The velocity vector will change direction and will lengthen. The position vector will change direction and shorten. And so the problem becomes very sophisticated. You probably didn't notice it at all, but so far all of the Newton's laws problems that you have solved have involved situations where the acceleration is constant and therefore the force is constant. But here is Isaac Newton, the creator of the thing in the first place, forced to consider a problem where neither the force nor the acceleration are constant during the motion. As it happens, there was no mathematics at the time available to solve such a problem. So Isaac Newton had to go ahead and invent it, along with a German mathematician whose name was Gottfried Wilhelm Leibniz. Isaac Newton invented calculus, a mathematical construct that it would make it possible for him to solve such a problem and to determine the shape of the motion of orbits caused by forces that change over time. The thing is, what do you choose for your force? In order to solve the problem, Newton first has to understand, what does he expect the nature of such a force to be? Newton realized two very important ideas. The first, I think, is quite easy to understand. The second is a little bit more sophisticated. Newton begins thinking about this force of gravity, which at the moment is unknown. And he says, what must the force of gravity depend on? Well, he had already considered the idea of action-reaction, when two objects exert forces one upon the other. They are equal in magnitude and opposite and in direction, and also their natures are the same. So near the surface of the Earth, when gravity exerts a force on an object, according to Newton's own principles, that object must exert an equal and opposite force back on the Earth. That means that when the Earth exerts a gravitational force on you, you exert a gravitational force back on the Earth. At first it sounds impressive, but because of the mass of the Earth is so extraordinarily large, when the motion happens, the motion is chiefly that we observe is chiefly your motion, because the Earth's mass is so large that its acceleration is fantastically small, and the Earth moves imperceptibly when you jump up and down on it. Nevertheless, the gravitational force between you and the Earth is equal and opposite. Well, the gravitational force that the Earth exerts on you is what we describe as your weight. If we increase your mass, we know that your weight increases. Logically then, if we were to increase the mass of the Earth, the gravitational force should also increase because of the symmetry of Newton's third law and the principle of action-reaction. Therefore, Newton supposes that this force of gravity that he's going to create should probably depend on, and here I've written, is proportional to, the product of the masses, m1 times m2. That way, if I increase one mass or the other, or both, I would increase the magnitude of the gravitational force observed. The second idea that he has is that the gravitational force should diminish as 1 over the square of the distance. He imagined that as you got further and further away from the Earth, say, or the Sun, depending on what system you're trying to describe, as you get further and further away from a body, its gravitational influence should decrease. It shouldn't be infinite in extent. He has no reason necessarily to believe that. It just sounds like a natural principle that has a ring of truth. And that's not surprising, because there are a lot of phenomena that decrease over distance in this way, phenomena that Isaac Newton would have been aware of. For example, if I observe the light that is produced by a candle, I find that if I'm very close to the candle, it appears to my vision to be very bright. We call that the luminous intensity, or simply the intensity of the candle. As I back away from a candle, the intensity decreases as a function of distance. And as I backpedal further and further and further and further away, the candle appears dimmer and dimmer and dimmer and dimmer and dimmer until I can barely see it there on the horizon. The reason for that was well known to Isaac Newton, and it's fairly simple to reason out. Here I've drawn a candle with some rays of light going from it. I've drawn a circle, the innermost circle there, that represents the sphere that I can see light from. Now, of course, the candle doesn't emit light downward, and so I haven't shown that. But imagine if it was just a point of light. It emits light in all directions, and so that light is passing through a sphere. Consider the inner sphere. There's a certain amount of light passing through that sphere, and that light has associated with a certain quantity of energy, certain luminosity. And so I can describe a certain energy per unit area, which we call the intensity of the light. And that intensity is the light spread over the area of that inner sphere. Now I've drawn a second sphere that is twice the radius of the first sphere. Now I consider the light that passes through that surface. It's the same amount of light. However, because the sphere is larger in radius, the area of that sphere has increased. In fact, the area of a sphere goes according to 4 pi r squared. So if a sphere is doubled in radius, its area is 4 times larger. Because the area appears in the bottom of the intensity equation, the intensity of the light has decreased by 1/4. We call this a 1 over r squared relationship. The light of the candle diminishes so that when I'm twice as far away, it's 1/4 as bright. 3 times further away, it's 1/9 as bright. 4 times further away, it's 1/16. Because the Earth is a sphere, and the gravitational interaction certainly appears to be spherical, people walk upright everywhere on the surface of the Earth, Isaac Newton imagined that the gravitational intensity would likely work the same way. If gravity were to diminish over distance, it would likely diminish according to a 1 over r squared law, because the gravitational influence was distributed over the area of a sphere, whose area was proportional to the square of the radius. So Isaac Newton has an idea of how he thinks the gravitational force should work. He imagines that it should be proportional to the product of the masses and inversely proportional to the square of the distance. But how does he prove that that's so? Well, what he has to do, the task at hand, is to say, let me assume that the gravitational force has this nature, and ask the question, what would be the shape of the orbits that would be caused by such a force? So he takes his force, and he applies his new mathematics of calculus and derives the shape of the orbits and finds them to be elliptical. It is a very, very challenging mathematical proof, and so you won't see me demonstrate it here, but he succeeded at that. He showed that if the force has a nature of 1 over r squared, that the orbits of the planets are elliptical, and Kepler had already demonstrated, based on observational evidence, the motion of the planets in the sky, that the orbits were elliptical. And so this revelation is achieved by Isaac Newton, where not only do we understand that the motion of the planets around the sun are ellipses with all of the behaviors that Kepler had observed, but now we understand why they move as they do, because the nature of the gravitational force is described by Newton as a universal gravitational law. That universal gravitational law is a little bit unfinished, because what Isaac Newton is telling us is that he has verified, using calculus, that the force of gravity is proportional to the product of the masses and inversely proportional to the square of the radius of the orbit. What's missing is the equality. We need to do some experiments to find out what the exact relationship is, which turns out to be quite simple. All you have to do is get a lot of mass together, and in a very, very sensitive way, an experiment that was done by a fellow by the name of Cavendish, measure the amount of force in a laboratory experiment, collect a bunch of data, and find the constant of proportionality. That constant of proportionality is revealing, and it allows us to write Newton's universal gravitational law in its complete form. The force of gravity is equal to the universal gravitational constant, the product of the masses, divided by the distance between their centers, squared, where the universal gravitational constant is determined by experiment to be 6.67 times 10 to the minus 11th, with units of Newton meters squared per kilogram squared. This is a revelation. This universal gravitational constant is extraordinarily small, 10 to the minus 11th. That means that the force between everyday objects is so fantastically small that you would never be able to measure it. For example, if I have two 1 kilogram masses and I hold them 1 meter apart, then the equation is simple to calculate. It's 1 times 1 divided by 1 squared is 1 times the universal gravitational constant, 6.67 times 10 to the minus 11th newtons of force, which is absolutely unmeasurable. Gravitational forces don't become large and create large effects until you have situations of very large masses, which is why the Earth exerts large gravitational, creates large gravitational effects, but I can't just simply pick up an apple and throw it around myself and let it orbit. That does not happen, because the force between me and my lunch is extraordinarily small. You might say at this point, well, hang on a second. You just heard you say, that the force of gravity on an object is what we call an object's weight. Well, in my study of physics up until this point, I've been calculating the weight often by simply stating that the force of gravity on an object, what I call its weight, is mg. I've drawn a dozen free body diagrams where the weight vector mg directed downward. So the force of gravity is equal to mg, where g is equal to 9.8 meters per second squared. And now you're telling me that the force of gravity is something different. Well, the answer is yes. I'm telling you that the force of gravity is something different. This idea that the weight of a thing is equal to mg makes an assumption. It makes an assumption that g, the acceleration due to gravity, is 9.8 meters per second squared everywhere. In fact, it's not. As you go away from the surface of the Earth, the acceleration due to gravity decreases. And so this, using mg as the weight, is a thing that we do only near the surface of the Earth. If I go from the ground to the top of a building, the acceleration caused by gravity doesn't change much. It doesn't even change enough for the basic experiments that one would do in an introductory course in physics to change results by any measurable way. However, as you go further and further and further away from the surface of the Earth, the acceleration due to gravity does in fact decrease. If you go all the way up 100 kilometers above the surface of the Earth, where the International Space Station orbits, you find that the acceleration has decreased all the way to, I think, about 8.85, depending on where you are in the radius. And so it decreases. And it's decreasing as 1 over the square of the distance. And that is easy to demonstrate. We make the claim that the force of gravity, the weight of a thing, is m times g. But according to Newton's third law, we know that it's an action-reaction thing. So when I say mg, which thing? Let's say that it's mass number 1. So mass 1 times g is the weight of mass 1. But I've just realized that there's a universal gravitational law that says that this force is the universal gravitational constant g. The product of the mass is m1 times m2 divided by r squared. Well, you see, on the left-hand side and on the right-hand side, the m1s, in fact, cancel. And so I can write that g, lowercase g, is equal to the universal gravitational constant, m2 divided by r squared. You say, well, wait a second. I know what g is equal to. G is equal to 9.8 meters per second squared. Well, not everywhere. It's not. And so now, to calculate the g, for example, caused by the Earth, I have to go around and do the calculation. The further I get from the surface of the Earth, the smaller the value for g. Let's imagine for a moment that we don't know that near the surface of the Earth, the acceleration due to gravity is 9.8 meters per second squared. We'd like to use the universal gravitational law to calculate it. Here I have our equation. G is equal to g, capital G, m over r squared. For the mass, I'm going to use the mass of the Earth, because I imagine here it's the Earth that is creating the gravity that I'm interested in. For the radius, I need the location from the center of the Earth to the point where I'd like to know what the value of g is. Here, I'd like to know what is the value of g at the surface of the Earth. The distance between the surface of the Earth and the center of the Earth turns out, coincidentally, to be the radius of the Earth. So now I'll plug some numbers into this thing and get calculating. The acceleration due to gravity at the surface of the Earth should be the universal gravitational constant, 6.67 times 10 to the minus 11th, multiplied by the mass of the Earth, which happens to be 6 times 10 to the 24th kilograms, divided by the radius of the Earth squared, which is 6.4 times 10 to the 6th squared. So many numbers, so many numbers, so many numbers. And when you put this into your calculator, you may find yourself all thumbs trying to get a right answer out of this. I recommend that you have a look around on the face of your calculator for the EE function. 2 capital E's right next to each other, which is how you do exponential or scientific notation on your calculator. You have to be a little bit cautious here, because using your calculator imprudently could result in wrong answers, which is why you might choose to do a rather clever physicist thing and examine the powers of 10 of the calculation first. Here's how I proceed. I know that when I multiply powers of 10, I add the exponents. When I divide powers of 10, I subtract the exponents. Therefore, ignoring all of the leading numbers, 10 to the minus 11th multiplied by 10 to the 24th is 10 to the 13th. So the numerator of this calculation is 10 to the 13th, divided by 10 to the 6th squared, which is 10 to the 6th, times 10 to the 6th, which is 10 to the 12th. So I have my numerator, 10 to the 13th, divided by my denominator, which is 10 to the 12th, which tells me that this calculation is going to work out to be 10 to the 1st. Now, All I need do is go ahead and calculate the lead digits. 6.67 times 6 divided by 6 squared, which works out to be 0.98 times 10 to the first, which gets me the answer that I expected all along, that the acceleration due to gravity near the surface of the Earth is 9.8 meters per second squared. And so here we have the universal gravitational law. The force of gravity is equal to G m times m over r squared. Notice curiously here that I've written a lowercase m multiplied by a capital M. This is a style thing that I like to do because I find in most cases when I apply the universal gravitational law, I'm applying it to a situation where a small object, like myself, or a satellite, or a moon, or a planet, or an asteroid, is orbiting a very large object, like the sun or the Earth. And so I find it convenient to write this in a way where I have a small object and a large object. The small object naturally being the lowercase m, and the large object being the capital M. You don't have to adopt this habit, but I find that it's useful in problem solving to keep myself organized, because I might inadvertently cancel an M in algebra that should not be canceled, and so I would get mysterious results. The universal gravitational law, and a subset of that, the acceleration due to gravity, is g, the mass of the planet, divided by the distance from the center of that planet squared. Universal gravitation provided by one of the greatest minds in the history of mankind, Sir Isaac Newton.